Welcome dear students into the class of number theory, and today in this video we are going to start with a new chapter, and the name of the chapter is continued fractions. So we are going to start with this chapter, continued fractions, which is a part of number theory. So let us start with the definition. What is a continued fraction, how to define it, and how to proceed on to the various theorems. So if n is a positive integer and x naught, x1, x2 and so on, xn are real numbers, or you can say positive real numbers, except for x naught. That means this x naught may be positive, may be negative, may be zero. Rest of the numbers x1, x2 and xn, these are positive real numbers. Then the number x naught plus 1 upon x1 plus 1 upon x2 plus 1 upon x3 plus and so on, and you will get at the last plus 1 upon xn. This number is called a continued fraction. It is called a continued fraction. Here it is to be noted that leave the first part. For the rest, everywhere you are getting this numerator as 1. This is 1, this is 1, this is 1. In every fraction, the numerator is going to be 1. And this number, this expression, this is called a continued fraction. Moreover, if these x1, x2, xn, these are, I have said these are positive real numbers. If these are positive integers, then the same expression will be called a simple continued fraction. Simple, or you can say simple finite continued fraction. Finite because the xn and this n is fixed. If it is going on continuously up to infinity, then it will be called an infinite continued fraction, simple infinite continued fraction. But here I am taking the case where n is fixed. In starting I have written where n is a positive integer, and this 1 over xn is the last term of this expression, and this expression is called a simple finite continued fraction. So it is the basic definition of a simple continued fraction. Moreover, another thing is there to be noted, that these x0, x1, xn, x3 and so on, xn, these are called the partial quotients. These are called the partial quotients of this simple finite continued fraction. And it can also be simply expressed as x0, then semicolon, and then x1, x2, x3 and so on, xn. So this is the notation to write a simple finite continued fraction. One thing is to be noted, that this x0, this is the integral part of this simple finite continued fraction. For example, we will take some examples, we will take some questions, and then you will understand clearly what a simple finite continued fraction is, how to obtain it if some rational number is given, and if some simple finite continued fraction is given, how to obtain the corresponding rational number. So let us move forward with some easy examples. So let us have this number 7 upon 23. I want to convert this number into a simple finite continued fraction. And how to do that? First of all, this is 7 upon 23. This is a fraction. This is a number which lies between 0 and 1. And if a number lies between 0 and 1, what is its integral part? Definitely the integral part is 0. So it can be written like 0 plus 7 upon 23. And then this is 0, this is okay, this is your x naught. This is 7 upon 23. You can write it as 0 plus 1 upon 23 by 7. Take this 7 from numerator to the denominator of the denominator. And now this is 0 plus 1 upon. Now concentrate on this number 23 by 7 and try to convert it now to a simple finite continued fraction. So this 23 by 7, you know what is its integral part? The integral part is definitely 3, because if you divide 23 by 7, the quotient obtained will be 3. So this number can be written as 3 plus 2 by 7. So this is the integral part and the rest of the number. For the rest of the part, repeat the procedure. So that means you have to write 0 plus 1 upon 3 plus 1 upon 7 by 2. 1 upon 7 by 2. And now concentrate on this 7 by 2. This 7 by 2 is once again a number which is greater than 1. So definitely its integral part will not be 0. What is its integral part? Its integral part is again 3. Because if you divide 7 by 2, the quotient obtained will be 3. So you can write it as 0 plus 1 upon 3 plus 1 upon 3 plus 1 upon 2. And when your fraction, when your this number has 1 in the numerator, your job is over. So what this number 723 as a simple continued fraction is 0, that is your x naught, semicolon, and then the numbers are 3, 3, 2. So this is 3, 3, 2. And if 0 is here, then that means this number is less than 1, because the integral part is 0. So this is one example. Let us have another example, because 2 or 3 examples will give you a very good view about the simple continued finite fractions, and then you will be able to handle the questions related to these. Let us have another number. Suppose I am writing here 51 upon 11. Now here the integral part is not 0. If you divide 51 by 11, the quotient obtained will be 4. So it can be written like 4 plus 7 by 11. Now 7 by 11, treat it as the main rational number which you want to convert into the simple finite continued fraction. So what you have to do now, you have to write it this 7 by 11 as 1 upon 11 by 7. That means take this 7 from numerator to the denominator of the denominator. And now concentrate on 11 by 7 in the same way. So what you will get? For 11 by 7, your integral part is 1. So it can be written as 1 plus 4 by 7. And repeat the process. So it is 4 plus 1 upon 1 plus 1 upon 7 by 4. And this 7 by 4, once again, it has an integral part greater than 1. In fact, it is having integral part equal to 1, not greater than 1, but it is equal to 1. So you can write it as 4 plus 1 upon 1 plus 1 upon 1 plus 3 by 4. Still you are not having 1 in the numerator, so you are to proceed further. This 3 by 4, take this 3 to the denominator of the denominator. So it will become 4 plus 1 upon 1 plus 1 upon 1 plus 1 upon 4 by 3. And now concentrate on this one, 4 by 3. This 4 by 3 once again has integral part equal to 1. So you can write this 4 by 3 as 1 plus 1 by 3. And since you are having 1 here in the numerator, your job is over, and this number 51 divided by 11 as a simple finite continuous fraction will become 4 as your x0, 4 as your x0, and then your x1, x2 are 1, 1, 1, 3. So it is 1, 1, 1, 3. This is the finite simple continued fraction for the number 51 by 11. Now this is one way. That means you have just converted a rational number into a simple finite continued fraction. Now reverse. If you are given a finite simple continued fraction, suppose you are given with 2 semicolon 1, 2, 3, 4, then which rational number it represents? The procedure is very easy. You just are going on the reverse process. You write this number as 2 plus 1 upon this 1 plus 1 upon this 2 plus 1 upon this 3 plus 1 upon this 4. And you are to simplify this expression. This 3 plus 1 by 4. This 3 plus 1 by 4, when you simplify it by taking LCM, it will become 13 by 4. 13 by 4 in the denominator. And this is 1 upon 13 by 4. So what it will become? It will become 4 by 13. So this portion will become 4 by 13. Once again, the same procedure. This is 2 plus 4 by 13. 2 plus 4 by 13. If you take LCM, you will get 30 by 13. But 1 upon 30 by 13. And 1 upon 30 by 13 is 13 by 30. So it is 13 by 30. And now look at this portion and repeat the procedure. Take LCM 30, you will get 30 plus 13, 43 by 30. But 43 by 30 in the denominator, 1 upon 43 by 30. 1 upon 43 by 30 will become 30 upon 43. So it will become 30 upon 43. And now it's very easy. You are just to take LCM, you are just to simplify. So it is 86 plus 30, 116 divided by 43. So this is the rational number which is being expressed in simple finite continued fractions as 2, 1, 2, 3, 4. So this is how to convert a rational number into a simple finite continued fraction, and conversely. There is a theorem which says that every rational number can be expressed as finite simple continued fraction, and that we are going to take now. Every rational number can be expressed as finite simple continued fraction. Every number. So let us start with some number. Let A upon B be any rational number. So what we are to show? We are to show that this A upon B can be expressed as a finite simple continued fraction. And it's very easy. So you are having A upon B. Let it be X. Let it be X. It is a rational number. Definitely it will have some integral part. It will have some fractional part. So let X naught be the integral part of A upon B, and the rest of the numbers definitely will have some denominator will have some numerator because the rest of the number is a fraction. So what you will get? You will get this a upon b is x naught integral part plus fractional part. Fractional part normally we write in these brackets x. So this is a fraction, and if it is a fraction, what kind of a number it will be? What kind of a number it will be? It will be if you divide your a upon b. If you divide a upon b, x naught will be here because x naught is the integral part, and there will be some remainder. And remainder, suppose it is r1. Suppose it is r1. By division algorithm, your a is b into x naught plus r1, and divide throughout by b. What you are going to get, a upon b is x naught plus r1 upon b. So this a upon b is your x naught plus r1 upon b. Since you have divided by b and obtained remainder r1, definitely r1 will be less than b. So r1 is less than b, and r1 is less than b. You can write this r1 upon b as 1 upon b upon r1. And now repeat the process. So repeating the process, what you will get? X naught plus 1 upon, once again divide b by r1. Definitely you will get some quotient and remainder. Quotient means the integral part. So integral part, say it is x1 plus remainder, suppose it is r2. So what you are going to get? You are going to get r2 divided by r1. R2 divided by r1, and this time, since your division is like this, you are dividing b by r1, you are getting here x1, you are getting here r2. So dividing by r1, if r2 is the remainder, r2 will be definitely less than r1. So r2 is less than r1. Take r2 into the denominator of the denominator. So it is 1 upon r1 upon r2. And repeat the process again. So repeating this process of x0, x1, then you will get x2, then you will get x3, then you will get x4, and so on. And at some stage, this process will terminate. Why? The reason is you are having in the first division. Look into the divisions, what you have done in the divisions. In the divisions, at the first step, you are having a is equal to bx0 plus r1. At the second stage, b is equal to r1 x1 plus r2. Then r1 is equal to r2 x2 plus r3. As your a is greater than b is greater than r1 and so on, similarly here your r1 will be greater than r2 is greater than r3 and so on. That means this r1 is greater than r2 is greater than r3 is greater than r4 and so on. So that means it is a decreasing sequence of positive integers. And if you are having any decreasing sequence of positive integers, it will definitely terminate at some stage, and the number obtained at the last will be 1. And suppose that stage comes when you are having xn minus 1 plus 1 upon xn. You have converted your rational number a upon b into your simple finite continued fraction as x0, x1, x2 and so on, xn. So that means every rational number can be expressed as a finite simple continued fraction, what I wanted to show. Then the questions of simple continued fraction, sometimes they occur in a different form. It has a different look, but the procedure is same. For example, suppose in your examination there is a question which says that x plus 1 upon y plus 1 upon z plus 1 upon t is equal to 37 upon 10. Find x, y, z and t. So that is nothing to worry about. Actually, this here x, y, z, t are integers. It will be given to you that your x, y, z, t are integers. So what is your x? X is in fact the integral part of 37 by 10. So integral part here is 3, because if you divide 37 by 10, then remainder obtained will be 3. So this 37 by 10 can be written as 3 plus 7 by 10. Now this is integral part on the left hand side, this is integral part on the right hand side. Comparing both sides, your x is equal to 3. And if x is equal to 3, x and 3 can be removed from both the sides. X and 3 can be removed from both the sides, and take reciprocal now. Taking reciprocal, y plus 1 upon z plus 1 upon t is 10 by 7. And once again, 10 by 7, the integral part is 1, so this number can be written as 1 plus 3 by 7. Now integral part on the left hand side is y, integral part on the right hand side is 1, so y is equal to 1. And if y is equal to 1, then they can be cancelled out. That means they can be removed further. And once again, reciprocate both sides. Reciprocating z plus 1 upon t is 7 upon 3. And 7 upon 3, your integral part is 2, so you can write it as 2 plus 1 upon 3. And now just simple comparison will give you z is equal to 2 and t is equal to 3. So z is equal to 2 and t is equal to 3. This is a solution of the given question, that x plus 1 upon y plus 1 upon z plus 1 upon t is equal to 37 upon 10. So this type of questions will be there in the chapter of simple finite continued fractions. We will continue in the next video with more theorems, with more results, with more about simple continued fractions. Till then, thank you. Thank you once again.